Hello, and welcome to Water Quality. In this video, I'm going to go over the carbonate alkalinity endpoint. This is the point at which essentially all of the hydroxide has been converted to water. There's not very much hydroxide left. And essentially all of the carbonate has been converted to bicarbonate, but it hasn't yet been converted uh, to carbonic acid. So first of all, let's do a charge balance of a sample of natural water containing carbonates and try to think about this as a titration in the lab. So we're going to do a charge balance before we add any acid to our sample. So on the positive side, we'll have conservative cations. And I'm going to put a 0 to represent that this is before the addition of acid, and then hydrogen ion. On the negative side, we'll have hydroxide, bicarbonate, carbonate, and also our conservative anion charges, so CaCs. And I'll put a knot here, a 0, to represent that this is before we add any acid. Now, we've essentially derived the alkalinity equation again, and I'm going to call this alk old to represent the alk before I add the acid. And this is the difference between the conservative cation charges and the conservative anion charges. And then we have the definition of alkalinity over here, the bicarbonate, carbonate, hydroxide, and then our anti-acid neutralizing species hydrogen ion. Next, we're going to add acid until, thinking about a titration, until the alkalinity is to the point where there's 1 CtCO3 equivalence of acid neutralizing capacity left. So we have the capacity to go all the way to convert the bicarbonate to carbonic acid. So when we do that, we can write a new charge balance, and I'm going to call this alk new. And this is our CCCs haven't changed, and the CACs also haven't changed, except that we have to add, or in this case subtract, because the anions are subtracted on this side of the equation, the chloride that's being added as the result of the hydrogen or hydrochloric acid addition. And so this is our alk new, and this is going to be equal to 1 CtCO3. And this is equal to the bicarbonate, the carbonate, the hydroxide, and then minus the hydrogen ion. So a potential source of confusion here is that in my first charge balance, I have 1 pH. I have the initial sample pH, and then when I titrate it down to the point where I have 1 CtCO3 equivalent of alkalinity left, I'm going to be at a new pH, just like when we titrate in the lab. So the pH is different in these two charge balances, and also all of the carbonate species have shifted. Okay, so now I'm going to make a substitution here for my CtCO3, and I'm going to write out the CtCO3 expression, which is just H2CO3 star plus bicarbonate plus carbonate. So I'm just making a substitution for the CtCO3. And then this side of the equation is unchanged. So bicarbonate, carbonate, hydroxide, and hydrogen. Now I can start canceling things out. So the bicarbonate cancels out, one of the carbonates cancels out, and I can rewrite this as carbonic acid. And I'm also going to put the hydrogen on this side of the equation. And then I'm left with my hydroxide and then one of the carbonates. So this is actually the proton condition for this endpoint, and it's something that I can find on the graph. So I want to find the point on the graph where this is satisfied. So I'm going to go ahead and move this down so that we can see the equation when we look at the graph. And one of the things I want to point out in this graph is that I have an example here. This is a log CPH diagram for the carbonate system. And in my example, the CtCO3 is 10 to the minus 2.5 molars. So if your CtCO3 is different, this whole family of carbonate species lines is going to move up and down, and your crossing points will change a little bit. Although, unless your Ka values change here, your carbonate system crossing point should be the same. Okay, so I find this crossing point using the graph, and what I'm going to do is use this on the left side and use this on the right side. And on the left side, I'm just going to follow down, follow the dominant species. So I'll follow this, and I follow the dominant species, and my summation of these two things is just a little bit above the dominant species, and that's because this is a log graph. Okay, so now I switch from having hydrogen ion be the dominant species to carbonic acid. Okay, and then on the right side, hydroxide is going to be the dominant species. And then at some point, this switches over to the carbonate. So now carbonate is the dominant species. And I follow down on the left and right sides until I hit the crossing point, which is right here. And it looks like it crosses at about pH is equal to 8.3. And that is my endpoint for the carbonate alkalinity.